Everyone. Today we'll be doing DeMorgan's theorem. So DeMorgan's theorem, I'll show you where it's used. But DeMorgan's theorem has two theorems. So the first one, we'll start with the first one, right? Where it says is, if you read the definition, you don't really have to remember the definition. Mostly if you remember the equation, that is much better, I think. Yeah. So let's just so it says first theorem states that the complement of a or sum of two or more valuable variables is equal to the and product of the individual complement. So if we say complement of or sum, so this complement of or sum, you can say it's something like this. You have your OR gate, right? And to get the complement, you put that circle. So this becomes a NOR gate, right? Then you have your A and B, and then we call this A plus B not, or complement of A plus B. So this is what they call complement of or sum, right? So just remember that. So this is the complement of or sum. Let me just draw it on the top, so it's much better. B, this is your NOR gate, and then again A plus B not, right? So this says complement of the OR sum is equal to the product of and product of the individual complements. So meaning they're saying is A plus B not is same as A naught times B naught. So A complement times B complement is same as A plus B complement, right? And then this diagram will look something like, so as you can see, there is multiplication. So we are working our way back. So first we'll have our AND gate. So we'll have A complement times B complement. Then one will be A complement, other one will be B complement. So that means we need a NOT gate here and a NOT gate. Yeah, so that becomes A, B, right? So this NOR gate is similar to this logic diagram, and let's see if that is true with a truth table. So we have our A input, we have our B input, and we have our A plus B complement, and then we have our A complement times B complement, right? So it's going to be 0, 0, 0, 1, 1, 0, 1, 1, right? So there are two inputs, so we'll have four conditions here. So, and if you remember your truth table for, what do you call, for NOR gate, so this will be 1, 0. Let me use another color for this one. This will be 1, 0, 0, 0, right? And let's check if this one also gives the same output. So if we have A and B here, so if we input 0, 0, right? So you 0 goes in, so it's not yet, so that becomes 1. 1 here, so the output will be 1, right? So here we are correct, the output will be 1. Now if we say we have 0 and 1. So 0 goes in, that becomes 1. 1 goes in, this becomes 0. So 0 times 1 is 0, right? And if you do similarly process, so that will again give you 0, 0. So that means this statement is true, that a plus b complement is same as a complement times b complement, right? And also make sure when you are writing this, there is no line in between, right? So it breaks the line or it breaks the bar, then changes addition to multiplication or multiplication to addition, right? So, and similarly, you can have, let's say, 3 inputs like this: a plus b plus c, all of them complement, and it will be some similar to this. So we'll have a complement, b complement, c complement, right? So as you can see, they are not connected, they are separated. So that's your first theorem of DeMorgan's, first DeMorgan theorem, right? Now let's go to the second one. Now the second DeMorgan's theorem says similar things as the first one. So it says De Morgan's second theorem states that the complement of and product of two or more variables is equal to the odd sum of their individual complements. So if we check this statement here, complement of the and product, so that's the AND gate. So we'll have our AND gate somewhere here, right? And then we also have a complement, so that means this is going to be a NAND gate, right? So this is our NAND gate. So we have our input A and B, right? And then, sorry, B. And then our output will be A times B complement. And as you can see, it's A times B complement. So again, just remember, important to note that A and B complement, they are not the same as A times B complement. And similarly, B is not the same as A plus B complement. So A complement plus B complement is not same as A plus B complement, right? So just keep that in mind. So this is our, you can say, complement of the end product, right? Now this says of the end product is, again, you can check, is equal to the or sum of the individual complements. So it says is that A times B complement is same as A complement plus B complement, right? So here our diagram will be, as you can see, this addition there or sum. So first we'll have our OR gate, that is A complement plus B complement. Our input are A complement and B complement. Then we have two NOT gates to give our A complement and B complement. So this diagram here is same as this diagram here, right? So as you can see, DeMorgan's theorem helps us turn multiplication into addition and addition into multiplication. And as you move on and we see more examples, you'll see it's quite useful when you get stuck in some places, like to simplify a Boolean equation or something like that. Right. So mostly used in simplifying Boolean equation. And also you might have seen similar, and I will show you also, a similar thing is applied in our, what do you call, experiment 2, where you don't have your OR gate. So, but I'll do that at the end. Right. And let's do its truth table. So you have A, B, then you have your output, first one A times B complement, second one being A complement plus B complement. Right. Again, our truth table have 0, 0, 0, 1, 1, 0, 1, 1. And then if you remember the truth table for NAND gate, it was 1, 1, 1, 0. Alright. And let's see if we get the similar as this one. So first is 0, 0 input that goes in, so that becomes 1 and 1. And then if we add these two value, 1 and 1 is 1, the OR gate, right? So that is correct. Then again we check it's 0, 1, so that input goes, so that 0 is inverted to 1, that 1 is inverted to 0. 1 plus 0 is still 1, right? And if you carry on similarly, you will have 1, and if both of them are 1, 1, then this to invert to 0, so 0 plus 0 is 0. So as you can see, the DeMorgan's terms is also supported by the truth table, right? And similarly, it can have multiple inputs, so and it will still work the same. So for example, you have A times B times C. It will give still you can use DeMorgan's theorem on this, and then that will give you A plus A complement plus B complement plus C complement, even if you have 4 variables or any different variables. Maybe let's say this time if you have X, Y, you have W, X, Y, Z, right? Complement, correct? And that will give you W complement plus X complement plus Y complement plus Z complement, right? So this is your DeMorgan's theorem. So what you should remember, these two equations, they are very important. This one and this one. And if you understand these two equations, you can do a lot. Okay, so let's say we have our NAND details, the universal property of NAND gate and OR gate, right? So we are going to use this here. So this is where that comes in. So universal property of where NAND gate and NOR gate, right? So here meaning we only use NAND gate or NOR gate to represent all the three basic logic gates, right? And if you can represent the three basic logic gates, you can represent any digital circuit or a logic diagram, correct? And this is mostly used here to save money, like and if we just build one IC and use one IC, we can represent multiple circuit diagrams. We save money, so we don't have to build any other ICs, right? So that's the mostly case for this. And also just remember this will also be shown in like your experiment here, right? So let's start. So I will start with NOR gate first. So the question is, NOR we have NOR gate, and how can we how can we use this to show the basic logic gates, right? Which is not R and and alright. So let's say you have your NOR gate here, right? You have two inputs and an output, correct? Now you also have seen the Boolean rules and the equations we have done. So remembering from those rules and the equation, you connect these two inputs, right? So this becomes one input, correct? So we have A in going A input that. So therefore our output will be A plus A complement, right? And if you remember your Boolean rules, one of them, I'm not sure which one, right? Said A plus A will be A, correct? So we can substitute that, so that will be A not or A complement, right? And this A complement, if you see, it's similar to linear NOT gate. If you do it, so it's your A, that's your A complement, right? So using NOT gate, we already have built our uh, first basic logic gate, which is this is congruent or almost the same, which is not gate, right? So this is how we show not gate using NOR gate, right? Now let's do the other one. Now let's move on to our OR gate. So Now OR gate using NOR. Right. So if you check our OR gate looks something like this. Then we have our A plus B, which will be A plus D, right? So we want A plus B, correct? So how are we going to do A plus B? So let's say we draw our NOR gate, right? So this NOR gate output will be A plus B no or A plus B complement, right? So for us to get the A plus B, we have to remove this bar here, or this line. So we have to remove this line. How are we going to remove it? If you remember, this is a NOT gate, right? And this comes to also one of the rules from Boolean rules, if you remember. This rule where A not is A, right? So if you have one NOT gate and then the another one, so that will be A not A, then A not, which is A, right? So we want to do something similar. So we can make this line double. So what can we do here is you can add a NOT gate there, right? So here you will have A plus NOT, and then here A plus B not, right? And that is same of A plus B. Correct. So now we already got that A plus B, and then we can uh, no, but we only want to use NOR gate here, right? So we can change this OR gate using NOR gate, right? So we just need to change that. So that will be something like this. So your diagram will be something similar to this then. Or you have your NOR gate, then again your NOR gate acting as a NOT gate. You have A, B. Here you will have A plus B naught, and then your output here will be two lines A plus B equal to A plus B. So A plus B complement is same as A plus B, right? So as you can see, all get gives a not get, right? So we got this. Now, now we want to represent AND gate using no gate, right? Now we want to represent, let me just write the code. Represent AND gate using NOR gate. So again, and also remember now this is where DeMorgan's theorem comes in play as well. So we have our AND gate A and B input. We have A and B output, right? So how can we use NOR gate to represent this AND gate, right? So first thing we do is here, one thing we can do is we try to convert this multiplication into addition. So we need to convert this multiplication into addition, right? So converting this multiplication into addition. So this is where we'll use DeMorgan's theorem. So we have A times B, right? And if you remember this again, the second rule comes in play. A times B complement is same as A complement plus B complement, right? So we wanna do that. But now again, remember, and if you remember one of the rules which says A complement is same as A, right? So if we do this, AB complement is same as AB, right? We agree with that, correct? So now we can use this equation with. So what we can do is can say A is equal to A B complement, right? Now we have A B complement. Now if you look at this here, this equation, it's similar because we have this term A times B complement, which is this term here, right? So we have that. That so we can substitute, and we can substitute here A complement plus B complement, right? So we can say this will be A complement plus B complement, then again you will have that line because this line we haven't broken it here, right? So that remains passive. So we have converted our multiplication into addition, right? Hmm, correct. So now we can use this here to get our, now we can use this equation here to build our second diagram. So that means, well, A times B is same as A complement plus B complement not. So the equation logic diagram for this equation will be, so we have addition and then there is a complement on top. So that shows it's a NOR gate. So we use the NOR gate here. So that will be complement control back. So that means our input is A complement and B complement, right? And as you can see, these two are using NOT gate. And if you remember, we can represent NOT gate using NOR gate, which is something right. We join those two when our input is B A and B. correct? Hmm. So we will draw this diagram, right? Yeah. Now we have drawn this diagram, so yeah, which is same as having an AND gate. So this diagram is same as our AND gate. A, B, with and B. Right. So this was three basic logic gates using NOR gate. And now, whenever they ask you use NOR gate only, meaning you only use NOR gate to build a logic diagram, you can do that, right? Now we go to NAND gate. Mm, NAND gate. So that now we go to NAND gate, and now we will use NAND gate again, just to remind you how it looks like. We have A B. Your output will be A B. No. Well, so this is how your NAND gate looks like. So we'll use NAND gate to represent all the three basic logic gates. So NAND gate U, so NOT gate, um, presentation using NAND gate. NAND gate. So this is similar to exclude NOR gate. So we'll have our NAND gate here, and we just connect the two inputs, and then the circle that, so that becomes a NAND gate, NOT gate using NAND gate. So this is same as having a NOT gate. Right. So represent it using NOT gate. Yeah, we using to represent NOT gate using both of them. It's just much easier than uh, the other two, right? So yeah, it's much easier. Okay. So now we go to our NOT gate. Yes, why am I getting go? Okay. Now we go to our OR gate using NAND gate, right? So now we use to represent OR gate using NAND gate. And then sometimes they also use only, so represent OR gate using NAND gate only. OR gate using NAND gate only. So yeah, you do get something like that. And you will see this term also in experiment 3. And also this is also, as you can see, it's also part of your experiment 2 as well. So if you remember in experiment 2, uh, you needed to use OR gate, IC number, I think so it was 74LS32, which you didn't have, right? But you had an IC which is 74LS00, and this is a NAND gate IC. So this is a OR gate, that is a NAND gate, right? So we used, in this case, as you can see, so this is where it comes from. We used a NAND gate only to represent OR gate, even in your experiment too. Right, so let's see how did we do it. So OR gate equation, we already know it's A plus B, right? So we have A plus B. So we want to use NAND gate only to represent our OR gate. So how are we going to do this? Similarly, we used a NOR gate to the similar process. So first, if you remember, one of the rules was A plus B complement is same as A complement times B complement, right? Correct. And also, if you remember this rule, A complement is same as A. So meaning if we do something like this, A plus B complement is same as A plus B. Right, we agree? So we can do that. A plus B complement. Right. Now if you check this variable here, A plus B complement is similar to this variable here. Right, so that means we can substitute these two values with this one, right? So we can write A complement times B complement, right? So this is, now we are done. So this is our OR gate using NAND gate only. And so that means our equation is A plus B, which is same as A complement B complement, right? And then this equation will be its representation. First you have a big NAND gate, right? So your input is not A and not B. Then we need a NOT gate, so we can use two NAND gates again, right? So A input, then B input. So this becomes our NOT gate, that becomes our NAND, and that the combination of these NAND gates will give you your OR gate, right? So the DeMorgan's theorem, as you can see, is applied here, and this comes in handy when you have limited resources, right? Or maybe when you just want to use NAND gate only. In some cases, we do just to save money, so we don't have to manufacture different ICs, right? So that was your OR gate using NAND gate only. Now we represent AND gate using NAND gate, right? So AND gate is quite simple. You have your AND gate, you have your A and B, and then you have A times B, right? And we want to represent this using NAND gate only. So how do we do it? This one is, things are quite simple. First, let's just draw our NAND gate. So we remember it's A and B, so we have A and B complement, right? And then here you just need your OR gate, NOT gate, I mean, to make it A, B, complement. And if you remember, again, this Boolean rule, A complement is A. So this will be AB. And we remember we can use not, what do you call, this not gate can also be represented using NAND gate, something like this. Right. So our circuit diagram will be AB right. So here you will have your NAND gate that will be A times B complement, then the output here will be AB complement which is AB. So this is same as this, right? So this is your universal NAND gate and NOR gate, right? And most of the time we use, I haven't seen much question related to NOR gate. Mostly it's NAND gate only, and even if you see in your components, you only got NAND gate only, right? So, mostly you will see you will use NAND gate only to represent all the logic gates, right? And maybe another thing I can show you, it doesn't matter how many input NAND gate do you have. Let's say, for example, you have 3 input NAND gate, and if you connect all the input to the A, your output still be not A, right? Because this will be just A times A, and that is, and if you remember, A times A times A is still going to be A, right? Oh yeah, that's is for the NOT gate. So here for NOT gate, uh, yeah, your output here will be A and A. So if you remember one of the Boolean rules, A and A, so here you again another Boolean rule comes in action. A times A is A, right? So yeah, maybe let's just do an example. Have this logic diagram. Maybe you have your AND gate, right? And then you have a NOT gate that goes to a OR gate. Then you have your output, right? You have A, B, and C. Right, so red is A, or maybe this one is a simple diagram for now. Purple, then yeah. So we know we have our input A, B, so the output here will be A times B, right? Then we know our input C, output here will be C complement, and then if we add all these three together, it should be AB plus C complement, right? So we got our equation from the circuit diagram, right? Now the question is, we want to represent this equation. It's AB plus C, right? So we want to represent this equation using NAND gate only. So, meaning we only want to use NAND gate to build a circuit, right? So how are we going to do that? So that means NAND gate only. So that means we will have to do something here, right? So in NAND gate only, that means you must change all the addition to multiplication, right? So how are we going to do this? We have this addition here, right? As you can see. So let's just start. So the first thing we always do is whenever we start with something like this, NAND gate only, so we always write this equation into its basic form, then we draw two lines on top of it, right? And just to get started, because then when we have two lines on top of it, then we can start using DeMorgan's theorem, right? Correct, yeah. So here, what can we do? Let's try something. Here, what we can do is something like this. If you see, these two are already in multiplication, right? So we don't have to break these two, correct? So we can say this A and B, let A, B equal to X. If you remember in maths the way we do it, and then we leave C as it is, correct? So we can say, so this is already multiplication, so we don't have to change anything there. So we can take that out just to make our problem solving easy. So we said let A times B equal X. So we can replace that with X plus C complement. So that is going to be something like this, right? And as you can see, uh, this is much more like something similar to A plus B naught equal to A naught plus B naught. Do we agree? Yes? Yeah. Yes, right? So here what we can do is now we can change this multiplication into this addition, I mean, into multiplication using I made a mistake there. So that should be multiplication. Yes. Into multiplication using this theorem. So that will be, we can say X line times C line bar, then that big bar, right? So always make sure you account for all the complement lines, right? And then we can simplify this further. If you look at this C term, this reminds me of this rule again. A complement A, which is A, so we can say C complement is C, right? So our final answer can be X complement C complement, right? Both of them under one complement. So that will be uh, X complement times C complement. And then we can, sorry, then we can bring this variable here back as to replace with x. So we can bring this back. So this becomes AB complement times C complement. So as you can see, we bring back that AB. So now we have done this. So we converted this into this equation. We can say AB plus C complement into NAND gate only, which is A complement B complement C times C and everything complement, right? So now this is NAND gate only, right? And then if we draw its logic diagram using NAND gate only, so we know we have a big NAND gate, so that will be something like this. Our output will be A, B, and C, so we know one will be A, B complement, other one will be just C, right? So this input is just C, and that means this is a NAND gate again. So we have A and B. And as you can see, using NAND gate only, we also reduce the number of logic gates, because in the original one we needed 3 logic gates, but in this case we only need 2 logic gates, right? So this is same as you having this A, B, C, A, B, C plus C naught, right? So, yeah, and then I would recommend this might be confusing now, but as you practice on more practice, that will help you understand better, right? And maybe let's just do this example also using. So now we are using the same equation ABC plus C naught. We use now NOR gate only. So in this case, we change all the multiplication to addition, right? So now we only work with NOR gate only. So again, we have this equation A, B plus C naught, and we follow the same process where we have A, B plus C naught, and we put a line on top of it, right? 2 lines, correct? Now what we do is, so again, in this case now, we already have this addition, right? Correct? So we don't need to break this bar here, right? Or break this addition into multiplication, right? We only need to do it with these two here. So it will be something like this. Let's see. Let me just figure it out. So this is going to be, if we break this. So the first thing we can do, I think, so the easier one is, first we need to change this multiplication, right? This into multiplication. So let's, maybe because I'm thinking, how can we do this? It won't work because if we try to break it, it's already there, right? Addition is easier to break. So, okay. So I think we'll follow the same method. So we'll just say for now this equal, let a be equal x, right? So we just say it is x plus c naught, not, not, right? And then we break that down, so that will be not x naught times c naught naught, right? So we can say this is going to be ab naught c naught, right? So now this whole thing is multiplication, correct? And if you're confused, I'm just following the same procedure as the NAND gate. But first thing, I'm converting all the multiplication, all the addition into multiplication. Then it's easier to work with, right? Because it's harder to break a multiplication compared to addition, right? So what we do here is, now first thing we'll do is, now we'll break mm, 8, 8 times b complement and c complement. So now, what we can do is we can break this into, again, multiplication, but it will be much addition, I mean, right? So here we'll apply this one, this rule. AB complement is A complement plus B complement, right? Correct? So we can just say, so in this case we can say is, let A be complement. So now we can say AB complement equal Y. Let me just write that down so it's easier. So let AB complement equal Y. Right. So in this case, I'm just taking out the common factor. And this might be, maybe for now you might not understand it, but you sit down, you practice, that will make sense. Right. So we can say here is y times c complement, right? So we can change that using that. So that will be y complement plus C complement, right? So then we can replace that, substitute that AB complement plus C complement, and that will equal, now we have AB complement, so we can change that to addition. So A complement plus B complement, then complement plus C. Right, so this is the equation. I know it might be much longer. It looks a longer process because we are just uh, separating these two. So in some cases you only have to separate multiplication, so that is fine. You can only apply to one place, but you can work with both of them. So I would say when you have addition here, first change all the addition into multiplication, then change all the multiplication back to addition when using or NOR gate, right? So using NOR gate is a bit harder, so but yeah. So we can say is now AB plus C complement is same as this, and then our diagram will be something like this. So first we'll have uh, all of this added together. So this will be, I think, something like this. First you will have your NOR gate and NOT. Right. Sorry. So that's why we don't really use that much OR in NOR gate, because I think it becomes more confusing compared to NAND gate, right? But I'm just showing you this for example. I think so. It will be something like this. You have your NOR gate as a NOT gate. So this whole thing here, A plus B NOT plus C NOT. Then you need another two lines on top, right? Because it will go back to here. You have your two inputs, not so. Here you will have like A not B plus C, not in that whole line on top of everything. And but as you can see, NOR gate does make a lot of things more complicated. Then you have two additions, so that means you will have your C not here, then your two inputs will be A naught plus B naught C, all of them not, right? So again, so that means you will have your somewhere here NOR gate as well. Then you will have your two inputs A naught, B naught. Then you will have your NOR gate here again. Then you have your C input. And yeah. So as you can see, I think NOR gate is not that easy to work with compared to multiplication, which is NAND gate. So And the most of the questions you might be asked will be NAND gate mostly. Right. So yeah. So this is the diagram which is more complicated, right? So but again, you sit down, you try to understand how this works. Cool. Yeah, I think we are done now. Thank you.